Hello everybody and welcome to Mrs. Baker's Chemistry Corner. This is question 17 from the monster paper for the metals module. The periodic table can be used to classify elements. Group 1 elements react with cold water to form alkaline solutions. Place the group 1 elements, cesium, lithium, potassium and rubidium and sodium, in their order of reactivity. Well, we know as we go down the group of the periodic table that they become more reactive. So at the very top, we've got lithium, then we've got sodium, and then next comes potassium, and then we've got rubidium, and then we've got cesium, which is the most reactive. It would be easy to fall into the trap of putting these the wrong way around, and students often do that and lose valuable marks, which they knew the answer to for that silly error. So if ever you've got to put something in order of reactivity, always make sure that you are highlighting where is the most and the least reactive. Name the alkaline solution formed when cesium reacts with cold water. Well, any metal reacting with any cold water is going to make a metal hydroxide and hydrogen gas. So we're going to make cesium hydroxide. Group 1 elements have lower melting points than transition elements. Describe one other difference in the physical properties of Group 1 elements and transition elements. So the physical properties that are the standout ones, they're easy to remember, are lower melting and boiling point and lower density. So they've already done the lower melting and boiling point, so we're going to say lower density for group 1s. Notice how I've added 4 group 1s, because if you say lower density, the examiner doesn't know whether you mean that the transition elements have a lower density or the group 1s have a lower density. So you must quantify which one has the lower density in a comparison, or which one has the property in a comparison question. So group 7 elements are known as the halogens. Astatine is below iodine in group 7. Predict the physical state of astatine at room temperature and pressure. Well, as we go down the group, we've got fluorine, chlorine, bromine, iodine, and astatine. They get darker as we go down the group. So iodine is actually as dark as it can get. It's black and it's a solid. So definitely the physical state of astatine is going to be a solid. You can't get any more solid than a solid because they get darker and more solid. So it is definitely going to be a solid. Okay, some group 7 elements react with aqueous solutions containing halide ions. So we're talking here about displacement. And in displacement, the more reactive halogen will displace the least reactive halogen. When aqueous chlorine is added to aqueous potassium bromide, a reaction occurs. So in this case, we're adding chlorine by itself to the potassium with the bromide. So chlorine is the more reactive. So chlorine is going to displace the bromine. So we started off with chlorine as an atom, and we've ended up with chlorine as an ion. We started off with bromide as an ion, and we've ended up with bromine as an atom. Describe the color change of the solution. The original color of potassium bromide solution would have been colorless, because we know that group 1 metals form colorless aqueous solutions. The final mixture of the reaction vessel is going to be the color of bromine. So bromine is a nice orangey yellow color. Identify the species that is oxidized. Explain your decision. Well, in this case, the chlorine has gone from 0 to -1. So it has had a decrease in oxidation number. Decrease is the same word as reduction, and reduction is gain. And if I've been reduced, I am the oxidizing agent. The other side, I've gone from -1 to 0, so I've had an increase. An increase is oxidation. Oxidation is loss, and that would make me the reducing agent. So in this case, I just need to know which species has been oxidized. Well, that would be my bromide ions. The explanation why because it has lost electrons. You could also have got the mark for saying that there'd been an increase in oxidation number, but it's always safer to talk about electrons when you're talking about why something's been oxidized or reduced. Okay, so bromine monochloride, or BrCl, is made from a reaction between bromine and chlorine. The chemical equation is shown. So we've got bromine as a gas with chlorine as a gas, making bromine monochloride. Don't worry at all if you have never heard of bromine monochloride. That's okay. You just apply what you know about the halogens, and you just apply what you understand about, in this case, using the bond energies to calculate the energy changes. So it's asking you to calculate the overall energy change for the reaction using bond energies. So we're just going to follow step by step through. Calculate the total amount of energy required to break the bonds in 1 mole of bromine gas and 1 mole of chlorine gas. So 1 mole of bromine gas is a Br and a Br joined together. So it's 190 kilojoules for every mole. And for chlorine, it's 242 for every mole. So 190 plus 242 is 2, 3, 4. 432. So we're looking at 432 kilojoules to break those bonds. Okay, so step 2 is to calculate the amount of energy released when the bonds in 2 moles of bromine monochloride are formed. So in this case, we've got 2 moles over here. So a BrCl, so we've got 2 lots of BrCl formed. So we've got a Br with a Cl is 218. So we've got 218 times by 2. 218 times 2 gives us 436. Calculate the overall energy change for the reaction. Well, in order to calculate an overall energy change, we always do reactants minus products. So in this case, our reactants was 432. We take away 436. That gives us minus 4 overall. So we've ended up with a delta H of minus 4 kilojoules per mole. That one was nice and easy.